Okay, so hello again, everybody. It looks like that I was able to successfully pull most of you in here based off of the numbers I am seeing. Uh, and again, so now we have this sort of new session. We have this nice blank chat window over here that you guys can now fill as I go through this tutorial talk. And again, as I'm going through here, I will not be able to see the chat window. So keep that in mind. If there's a question that you'd like to ask me, use the Ask a Question button, and that'll be easier for me to go through those at the end. And if you're ever interested in asking the question face-to-face, if you want to come up onto the screen to ask your question, leave a little note in your question saying, I'll like to come on screen, or, on screen in parentheses, anything like that. That'll let me know to try to invite you onto the screen to ask that question rather than me sort of reading it off to myself. So with that, I will get started here. And what I'm going to talk about in this tutorial is sort of some terminology that's going to be important for the upcoming talks, mainly multi-stability and oscillations, and sort of how this terminology has evolved from very pure mathematics and is now being used in computational neuroscience and in neuroscience more generally, and how we need to understand these terms in different settings to be able to communicate correctly. So I'm going to start off with something that may be a little bit remedial for some of you guys. But again, we have a lot of different trainees with a lot of different backgrounds from a lot of different fields. So it's really important to make sure we're all speaking the same language. So the first word I want to define in our dictionary is a differential equation. Hopefully you guys have all heard of these before. These are just equations that relate a rate of change to some function of variables. So I'm relating the velocity instead of the position, right? So that's the very common way that this is used in introductory calculus courses. Differential equations are used to model things throughout computational neuroscience. The Hodgkin-Huxley equations, which are sort of the seminal proverbial example of a neural model, are differential equations. Now, one of the things that is very useful in understanding a differential equation, understanding what's modeled when you look at a differential equation, is looking for something called a fixed point. This is a set of variables for which this rate of change, or the differential equation itself, is equal to 0. This is sometimes called an equilibrium point, a critical point, a steady state. I'm going to try my best to stick with this fixed point terminology throughout this talk, but I'm sure I probably will mess up and use one of these other terms at some point, so I apologize in advance. And then again, what a fixed point is essentially, you can think of it almost as a balance point. If I start right at a fixed point, I'm never going to leave that fixed point. Why? Because there's no change. My rate of change, as modeled by the differential equation, is equal to 0. So I'm going to stay there always and forever, unless something else comes along and perturbs me and forces this system to start behaving in some new fashion. Now, these fixed points are typically classified as either stable or unstable. I'll describe those more in a second. You may also see in more complex systems these sort of intermediate classifications of something that's not quite stable or unstable. These are sometimes called a saddle node. Sometimes they're called semi-stable fixed points. We're not going to worry all that much about that for this introductory talk. We're going to focus on things either being stable or unstable. So the easiest way to think about this is, imagine that you have a series of hills and valleys, and you drop a ball and you see where your ball rolls and you see where your ball stops rolling. So that's essentially a nice way of thinking about these fixed points. So we have this nice little cartoon here on the side here. Very roughly, minus some constants and whatnot, I could describe this system with the differential equation shown here. Now, the first question you want to ask whenever you see a differential equation like this are, what are the fixed points? Well, so what makes dx dt equal to 0? Obviously here, that's going to be x1, x2, and x3. So those would be the 3 fixed points to this system. Now you might ask yourself, well, there's obviously something different about the x3 fixed point than the x1 and the x2 fixed point. The reason being x3 is unstable, while x1 and x2 are stable. Hopefully you can sort of see that from this cartoonish picture. The idea being, if I drop my ball perfectly at x3, it will stay there sort of precariously balanced. And if I just give it the tiniest little nudge either way, it will roll away from x3 and will go towards one of these other fixed points. The alternative is if I'm in the valley, represented by x1 or x2, and I give a little bit of a perturbation, the ball will roll around, but it will settle back down at x1. So a stable fixed point is something where if I perturb it, my system away from the fixed point, I should fall back towards it. And an unstable fixed point is a fixed point where if I perturb it, it will go away from that fixed point. Now, this is also an example of something called a multi-stable system. Very straightforward. There is 2 points of stability, x1 and x2. So this is a bistable or multi-stable system. And which one of these stable, steady states my system settles at depends on a lot of different things. It depends upon the initial conditions, where I drop the ball. It depends upon if there's some sort of perturbation going on in this system. And what I want you guys to keep in mind, I'm going to mention this a lot throughout these next 15 minutes, is that these behaviors can become super, super complex very quickly. This is perhaps the simplest example of multi-stability of a differential equation that I could give you. But if I say have a differential equation that has more than one variable or is nonlinear, all of these sort of crazy mathy terms that all mean more or less more complicated, then it becomes much more difficult to determine, is something multi-stable, what are those stable solutions, etc. Now, the last term we need in our dictionary here is bifurcation. So in these more complicated settings I just mentioned, we can get some situations where by changing one individual parameter, I can change the number and the stability classifications of these fixed points. And we say that if you can change a parameter to cause a sudden and significant change in the fixed points, a bifurcation has occurred. Now again, bifurcation theory is a whole complex field of mathematics, especially in these more detailed, complicated differential equations. It is not always straightforward to find out if a bifurcation has occurred and what the consequences of that bifurcation are. Now, why are these terms, bifurcations and multi-stability, important to us as computational neuroscientists? Well, they actually can describe some of the behaviors we see in the brain quite well. So in my research, I'm very interested in understanding seizure initiation. And that's often thought of as a bifurcation in the dynamics of the brain. When you go between a nice, stable, healthy brain rhythm and a super oscillatory, hypersynchronous, hyperactive seizure state. That's a sudden transition between two very, very different states that we will often call a bifurcation just by looking at it. And there's also a lot of research that shows that there actually are bifurcations underlying that mathematically. And I'll talk a little bit more in detail later about what I mean about those sort of two different directionalities there. The other place where this often comes in is in the term oscillations. We're all interested in oscillations. We know how important these are to understanding brains and brain rhythms. And what I'll show you in a sec is that mathematically speaking, these oscillations often arise out of bifurcations and out of these multi-stable regimes. So I want to show you two examples here of bifurcations in action. So this is something called a saddle node bifurcation. These blue curves are basically just potential paths that can be taken in this differential equation. And what you'll see is as this alpha value gets larger, once it hits 0 now and goes past it, these black and white dots appear. Those are the fixed points, one being a stable fixed point, one being an unstable fixed point. So we see here that as we change this alpha parameter for this particular differential equation, all of a sudden fixed points appear and start to move away from each other. So this is a sort of hallmark definition of what a bifurcation looks like in practice. Here's another example of a bifurcation. It's a little bit different. So we see that we're changing this B value here. These red swirls are the paths. And all of a sudden, right about now, we get this blue path that's actually its own closed loop. So that's something very distinct from the other paths that we've seen so far. And what we call that is a limit cycle. And you'll see it again pop up again as this animation starts. So limit cycles are closed loops that can arise out of the dynamics of a differential equation. And much like fixed points, they can be either stable or unstable. They can either attract everything to it or repel everything away from it. And also much like a fixed point, if you start on that limit cycle, you'll stay on that limit cycle forever. So imagine instead of being sort of stuck at the bottom of the valley, I dropped my ball onto a Hot Wheels car track that is now motoring the ball around the Hot Wheels car track. And nothing's going to knock that ball off that track unless I come in and break it apart or my dog comes in and bites it. Now, this is something that's really important in a lot of different settings. Again, the most typical being the Hodgkin-Huxley equations, where you get these limit cycles, which are shown through the periodic firing of a Hodgkin-Huxley neuron based upon this type of a bifurcation called a Hopf bifurcation. Now, it's worth pausing here to mention, once again, that things like stability and bifurcations in these more complicated, higher order, nonlinear, all these mathy term systems are their own branch of mathematical research. And how detailed you need to understand these things is very much up to you and what the goals of your research are. So don't feel any pressure now to go and take a class in bifurcation theory or anything like that. That may not be necessary for your particular research. What is necessary is that as computational neuroscientists as a whole, we're able to communicate with each other and we have some sort of shared verbiage. So if you read a paper that talks about a bifurcation or a multi-stability, you need to be able to know what that term means and also be able to read via the context clues whether it's meant in the pure mathematical sense or whether it's meant in a more descriptive phenomenological sense. So to give you some examples of that, I'll show you really quickly some results from some of my research in epilepsy. So one of the things that we've been interested in is inhibitory networks in epilepsy. And what we found is that if you take a purely inhibitory network and you give it some sort of perturbation, you can shift it from an asynchronous state to a synchronous state. And both of these states seem to be stable because they will persist as long as we run the simulation. So we observed this and we were able to use mathematical terminology to describe what's going on here. We said that these systems were bistable. So if we draw our parallel back to our graph from the beginning, basically one of these valleys is the stable state, one is the asynchronous state. And one of the interesting things we found was that if the network was more like a seizure network, more like an epileptic brain, we were more likely to have a perturbation that caused us to go from asynchrony to synchrony. So the way you can think about that in terms of our parallel is that when you're in a seizure state, the depth of this asynchronous node is significantly less, basically meaning it's much easier for me to push my ball out of the asynchronous well and into the synchronous well. So again, this was a case where we had a complicated network where we couldn't quite describe the system mathematically in a way that we could do analysis, use the mathematical tools of bifurcation theory of stability analysis necessarily. But we observed something that looked like bifurcations and looked like multi-stability and made a prediction that was probably had something to do with the underlying mathematics. The opposite can also be true, where we can use the mathematics to make a prediction about the biological system. So I'm going to go through this pretty quickly here because I'm already running out of time. But essentially, in this work that's currently submitted to scientific reports, we have a simple EI network, and we created a network that's simple enough that we were able to use mathematical tools to simplify things down. Once we simplified things down, we were actually able to use the tools of bifurcation analysis in dynamical systems to yield what's called a bifurcation diagram. So, oops, I clicked there accidentally. So I want you guys really to just focus on this top row here. On the left here, we have a system with low intrinsic noise. On the right, we have a system with high intrinsic noise. And you can see really quickly what the big difference here. It's this region at around an I value of 0.05, where we have multiple fixed points. These black lines are fixed points. So if I draw a vertical line up here, I go through 3 separate points on my graph, meaning there are 3 potential fixed points for that value of I naught. What that means is that it's possible to shift from one fixed point to another fixed point with some sort of perturbation. And doing that is probably going to yield a really significant difference in the dynamics of the system. What might those change in dynamics be? Well, it might be a seizure. And what we found is that these networks with low intrinsic noise were more likely to have this multi-stability than networks with high intrinsic noise. So we thought maybe that means that networks with low intrinsic noise are more vulnerable to seizure. And if we sort of go back to the more complicated network, we see that that is indeed the case. This red curve here is the low noise state. When we give it this sort of increase in current, we see this very hypersynchronous oscillations. But for the black curve where the noise is much higher, this increase doesn't really change much in the system. So here, we were able to use the mathematics to make a prediction about the dynamics of the system. So that's sort of the reverse direction of what I showed you before, where we sort of observed the system and made a prediction about the underlying mathematics. So just to conclude here, it's important to know these terms because they will come up in these talks we're going to hear today. They'll come up throughout the literature. And it's important to know what the setting is you're using these terms in. Are you either describing a biological system using this mathematical terminology, or are you doing mathematical analysis to make a prediction about the biological system using these mathematical tools? Both of these are equally useful and beneficial in computational neuroscience, but it's really important that as the computational neuroscience community, we're very clear and consistent, at least in our own work, in how we're using these papers so that they're going to be most easily read and absorbed by the rest of the community. So with that, we have a couple minutes for questions, or actually, I have maybe time for one question here. So Ashraya asked, I deal with bifurcation studies. I'm struggling to find the proper tool to plot my bifurcation graphs. If we are expecting only one bifurcation, then yes, I can do XPP out. But if there are 2 to 4 bifurcations, are there any good tools to use for this? That's a very good question. Unfortunately, the best tool I know is XPP for sort of graphing these bifurcation diagrams. And it is well known that, the more bifurcations you get, the more complicated things are because you're sort of leaving a 2-dimensional space, more or less. So the one thing I might suggest, and without knowing too much about your specific project, is it might be worth potentially looking at bifurcations in a more simplified setting, where you're only looking at 1 or 2 variables out of your whole network and looking at the bifurcations in that sense. That may limit things so that you're able to visualize the bifurcations in terms of 2 variables as opposed to all your variables. Or you may want to perhaps find some sort of measure that encapsulates a bunch of your different variables and is able to sort of summarize those into one setting. And it sounds like in the chat, a couple people have mentioned some potential tools, something called MatCont for MATLAB. Dimitri mentioned PIDS-tool, which I would imagine is a Python tool. So those are tools I'm not personally familiar with, but I'm sure you can check those out. So with that, I'm going to end this broadcast so we can go move into our first research talk by Sue-Ann Campbell. So you guys should be moving into that next talk momentarily.